The Sun has just displayed a phenomenon, both extraordinary and unsettling. A massive coronal hole has torn across its surface, releasing a high-speed stream of plasma directed toward Earth. At that exact moment, something equally mysterious occurred. Comet 3e Atlas, an interstellar visitor from beyond our solar system, vanished from every telescope. Soon after, Earth registered seismic activity. The immediate question scientists are asking is, what exactly happened? Was the comet destroyed, transformed, or simply concealed? And if it does return, what form might it take? As one celestial body fades from sight, another emerges into view. Comet Lemon, a frozen relic older than human civilization, now speeds through our skies. Experts explain why the next 2 weeks could prove pivotal. In October 2025, our star underwent a dramatic transformation that few noticed but many now study closely. Astronomers observed a vast transequatorial coronal hole opening across the Sun's magnetic field, a dark scar releasing streams of energy into space. Unlike ordinary solar flares that create auroras or minor satellite disruptions, this event was immense, bridging both solar hemispheres in a rare configuration with potentially profound consequences. Through this magnetic breach, the solar wind accelerated to extraordinary speeds of 700 kilometers per second. To visualize that, imagine particles racing at nearly 1.5 million miles per hour. This torrent of charged particles, electrons and protons stripped from atoms, rushed toward Earth in a direct, high-energy stream. Even more striking, the alignment between the solar wind and Earth's magnetic field was exact, creating optimal conditions for energy transfer into our magnetosphere. Scientists and engineers mobilized quickly. Power grid operators issued alerts, satellite teams prepared for interference, and photographers traveled north to capture the expected auroras. Yet amid this solar turbulence, something far stranger occurred. Comet 3i Atlas, only the second interstellar object ever observed in our solar system, disappeared as it passed behind the Sun. Just hours earlier, it was visible as a faint streak, carrying material from a distant star system billions of years old. Then it was gone, lost in the Sun's blinding glare and invisible to every telescope on Earth or in orbit. The timing of its disappearance, coinciding exactly with the solar event, was too remarkable to dismiss as mere coincidence. Earth's magnetic field was under siege, struck by the fastest solar wind in months, while at the same moment, our only visible interstellar visitor vanished behind the very star causing the disturbance. Scientists, cautious by nature and trained to separate coincidence from causation, chose their words carefully when asked if these events could be linked. Then, the ground began to move. Within hours of the solar storm's arrival, a series of magnitude 7 earthquakes rippled across multiple regions of the planet. Instruments recorded the violent shaking, the sudden release of tectonic energy long trapped within Earth's crust. Statistically, such quakes are not unusual. Earth averages about 15 of them every year, but the timing, several large tremors coinciding so closely with a powerful solar event, and the disappearance of an interstellar comet, triggered something deeper in human instinct, that ancient drive to find patterns and meaning in chaos. Could the Sun's magnetic onslaught somehow have influenced seismic activity? The prevailing scientific consensus says no. Tectonic plates move according to geophysical forces, not magnetism or solar wind. Yet, some researchers on the fringes of geophysics question that certainty. They point to statistical irregularities, showing slight increases in earthquake frequency during periods of intense solar activity. Their theories invoke subtle mechanisms, ionospheric coupling, minor variations in Earth's rotation rate, that remain unproven but persist in academic corridors and online discussions, whispered as possibilities not yet fully dismissed. The comet, however, holds the true mystery. Comet 3i Atlas earned its name as the third confirmed interstellar object ever detected entering our solar system. The first was 1I/Oumuamua in 2017, a long tumbling object that accelerated in ways standard physics struggled to explain. The second, 2I/Borisov in 2019, behaved more like a traditional comet, its icy core and predictable orbit offering reassurance. Then came 3I Atlas, discovered in 2025, plunging toward the Sun on a hyperbolic trajectory, too fast to be bound by our star's gravity, an unmistakable traveler from another system. Such visitors are invaluable to science. They are the only direct samples we have of material forged around distant suns, remnants of alien protoplanetary disks. Until humanity can send probes to other stars, every photon we collect from these objects carries irreplaceable data, clues about chemistry, formation, and the universality of planetary creation. When 3I Atlas slipped behind the Sun, our instruments went blind, cutting off that stream of cosmic information. Now, astronomers wait with one pressing question. When the comet re-emerges, if it re-emerges, will we still recognize it? Did the Sun's intense radiation, gravity, and magnetic turbulence alter it beyond recognition? Could it have fragmented, vaporized, or transformed entirely? The moment of truth is approaching, and the outcome could challenge everything we think we know about interstellar wanderers. The story of Comet 3I Atlas began like many celestial discoveries, through patience, precision, and machines that never sleep. Each night, automated telescopes scanned the heavens, searching for anything shifting against the fixed tapestry of stars. Among them was the Atlas Survey, short for Asteroid Terrestrial Impact Last Alert System, a global network of 4 robotic observatories designed to detect asteroids that might threaten Earth. But Atlas does not discriminate. Its sensors record every moving object in the sky, and in early 2025, they captured something truly remarkable. At first, it appeared only as a faint streak in images from Hawaii. Follow-up observations from other observatories confirmed motion, rapid motion. The object's trajectory revealed a hyperbolic path, its eccentricity greater than 1. In astronomical terms, that meant only one thing. This visitor was not bound to the Sun. It came from the depths of interstellar space, and after its close encounter, it would leave again. A brief traveller through our system before returning to the vast darkness between stars. The discovery electrified the scientific community. Telescope time, typically scheduled months in advance, was suddenly reprioritized. Researchers worldwide turned their instruments toward this interstellar messenger. Spectroscopy, the study of light emitted or reflected by the comet, became the top priority. Scientists wanted to know, what was it made of? Would its chemical fingerprint mirror the icy bodies native to our solar system, rich in water, carbon dioxide, and organic molecules? Or would it reveal alien chemistry, a signature of worlds formed around another kind of star? Early data raised questions. The comet's brightness didn't behave as expected. Typically, as a comet nears the Sun, its light output increases in a predictable way, driven by the sublimation of surface ice. Water ice begins this process near 200 Kelvin, vaporizing directly from solid to gas. Other volatile compounds like carbon monoxide and carbon dioxide can sublimate even farther from the Sun, sparking early activity. But 3I Atlas defied that pattern. Its light curve showed long, flat stretches, followed by sudden bursts of brightness, erratic pulses suggesting irregular releases of dust or gas. The coma, the cloud of vapor and dust surrounding the nucleus, appeared fainter than expected. The comet's dust production seemed unusually low for an object of its apparent size. Some astronomers theorized that its nucleus was unusually dense, more rock than ice, explaining its subdued activity. Others proposed the opposite, that it was a loosely bound rubble pile, its porous structure causing gas to escape unpredictably. Then came the problem of the non-gravitational forces. Comets don't move solely under gravity's pull. As their ices vaporize, jets of gas act like tiny thrusters, subtly altering their paths. These shifts are measurable but unpredictable, complicating trajectory forecasts. For 3I Atlas, those deviations were unusually strong. Orbit predictions required constant revision. Error margins widened. Astronomers became increasingly uncertain about when and where the comet would re-emerge from behind the Sun. There were even signs it might have fragmented before vanishing. Cometary nuclei are fragile, clusters of ice and dust barely held together by gravity. Under solar heating or tidal stress, they can split apart, leaving a trail of smaller fragments that continue along similar paths. Whether 3I Atlas had met, that fate was unknown. But as the data grew inconsistent and the light faded, one thing became clear. This interstellar traveler was no ordinary comet. Sometimes, when a comet begins to fragment, its coma reveals faint, multiple cores, bright spots marking the pieces breaking apart. Images of 3I Atlas hinted at just that, subtle asymmetries, stretched shapes suggesting the nucleus might already be coming undone. If fragmentation had begun before the comet vanished, the question became even more urgent. What would emerge from behind the solar glare? Perhaps a single surviving core, perhaps a trail of debris, or maybe nothing at all if the fragments had become too small to detect. Comparisons to earlier interstellar visitors were inevitable. The first, 1I/Oumuamua, was never conclusively classified as a comet. It displayed no visible coma, no dust tail, nothing to mark it as an icy body. Yet it accelerated away from the Sun in ways gravity alone could not explain. The leading theory pointed to outgassing of exotic volatiles, possibly carbon monoxide or molecular nitrogen, compounds capable of sublimating without producing dust. Alternative ideas, from light sails to alien probes, captured public imagination but found little acceptance among scientists who deal in measurable evidence rather than conjecture. The second visitor, 2I/Borisov, behaved more like a traditional comet. It developed a bright coma and tail, and its variations in brightness fit established models. Spectroscopic data revealed familiar compounds, water vapor and carbon monoxide, chemistry almost identical to comets born in our own solar system. In a way, that was reassuring. It hinted that the processes shaping distant planetary systems might mirror our own. But even Borisov showed signs of structural weakness near perihelion, its closest pass to the Sun, where images captured a fragment separating from the main body. A reminder that interstellar travelers rarely endure their journey through the inner solar system unscathed. Now, 3I Atlas was following a similar trajectory, plunging sunward, and it vanished at the most critical point. The geometry of solar conjunction, when an object passes behind the Sun from Earth's viewpoint, creates a temporary blind spot. Depending on the object's orbit and brightness, this period of invisibility can last for days or even weeks. For a faint comet already behaving unpredictably, that gap became a void of uncertainty, a black box where anything could happen unseen. The comet might be disintegrating, it might be brightening, or it might still be intact, simply hidden within the Sun's overpowering glare. Humanity could only wait. Modelling teams worked to predict outcomes using assumptions about the comet's size and composition. If its core was large and rocky, simulations suggested it would survive with modest erosion. If small and icy, it could vaporize entirely near perihelion, leaving behind only a fading mist of gas and dust. The uncertainty was vast. Estimates of nucleus size ranged from a few hundred meters to several kilometers, a difference that made every forecast little more than an informed guess. Astronomers began calling it the invisible interstellar traveler. Somewhere beyond the Sun's radiant curtain, hidden from every telescope ever built, a visitor from another star system was either surviving or dissolving, and no one could intervene. Each passing hour stretched the anticipation further, an eternity packed into mere days of waiting. The Sun is not a gentle star. Though it sustains life on Earth, up close it is a realm of violence, a churning ocean of plasma millions of degrees hot, where magnetic fields twist like coiled springs of energy. And when those magnetic structures snap, the release can be catastrophic for anything caught nearby. The coronal hole that appeared in October 2025 was the kind of event that keeps solar physicists on edge. Coronal holes are regions where the Sun's magnetic field opens outward into space rather than looping back to the surface. These open field lines act as conduits for solar wind, allowing streams of plasma to escape at high velocity into the solar system. Normally, solar wind moves at around 400 kilometers per second, but the flow from this particular hole reached 700 kilometers per second, nearly twice the usual speed, carrying far more energy, momentum, and potential for disruption. When a comet encounters solar wind at such velocities, the interaction becomes intense and unpredictable. Unlike Earth, comets have no protective magnetosphere. The charged particles strike the coma directly, the cloud of gas and dust surrounding the nucleus, and physics takes over in strange ways. Ultraviolet radiation from the sun ionizes the gases, producing electrically charged molecules. These ions react to magnetic fields, which are frozen into the flowing solar wind and drape around the comet like a cosmic cape. The result is a magnetotail, a glowing structure stretching millions of kilometers away from the sun, illuminated by ionized carbon monoxide and other molecules. The tail is dynamic, not passive. Turbulence in the solar wind makes it wave and flutter. Occasionally, it undergoes disconnection events, breaking off completely as a new tail forms. Observing these phenomena from Earth provides scientists with vital clues about both solar wind conditions and the comet's gas output. But what happens when a comet faces an exceptionally fast solar wind while already stressed by intense heating near perihelion? History offers some unsettling examples. Comet C/2012 S1, expected to shine spectacularly, disintegrated during its 2013 perihelion pass. Images from solar observatories captured it entering the sun's proximity as a bright object and emerging only as a dissipating cloud of dust. Its nucleus had fragmented entirely under the combined thermal and tidal forces. In contrast, Comet Lovejoy, a sun-grazing comet that passed within 140,000 kilometers of the solar surface in 2011, survived against expectations. Post-perihelion images showed its tail stretching millions of kilometers, fed by massive gas emission from a superheated nucleus. The exact reason for its survival remains partially unexplained, likely a combination of size, composition, and structural integrity, allowing it to endure conditions that should have vaporized it. 3I Atlas was not a true sun grazer like these examples, but it was entering a zone dominated by the sun's influence during an unusually intense solar wind. The pressing question became whether the combination of thermal stress, radiative heating, solar wind pressure, and potential pre-existing fragmentation would be sufficient to destroy it. Some researchers proposed more unconventional explanations. The electric comet model, advocated by a small group of plasma physicists, suggests comets acquire electric charges as they interact with the solar wind, and that electrical forces, not only thermal sublimation, drive activity. Mainstream astronomy has largely rejected this approach, noting that conventional physics adequately explains most observations. Yet proponents cite phenomena such as tail disconnection events and rapid changes in brightness as possible evidence that electrical interactions play a role in a comet's behavior. The hypothesis ventures further into the fringes, suggesting that intense solar wind events could generate charge separations within a comet's coma. Under certain conditions, these electrical imbalances might trigger sudden disruptions or even alter a comet's trajectory beyond what ordinary outgassing would produce. The evidence for such claims remains contested. The theoretical framework is incomplete, yet these ideas persist because they attempt to explain behaviors that do not fit neatly into standard models. When 3I Atlas vanished during a major solar wind event, proponents of the electric comet model saw potential validation of their theories. Mainstream astronomers, however, interpreted the timing as a coincidental overlap, dramatic but ultimately unrelated. Adding to the uncertainty is the simple fact that the composition of 3I Atlas remains largely unknown. Spectroscopic observations taken before it disappeared were limited, offering only a partial view of its chemical makeup. The comet could be dominated by water ice, like many familiar solar system comets, or it could contain primarily carbon monoxide ice, sublimating at much lower temperatures and activating far from the sun. It might even be rich in silicates and poor in volatiles, resembling an asteroid more than a typical comet. Each of these possibilities would respond differently to solar heating and solar wind interaction. If the nucleus is highly porous, nearly aerogel-like, thermal waves could penetrate deep, sublimating internal ices and causing catastrophic disintegration. If instead it is covered by an insulating dust mantle, gas release would be concentrated in isolated jets, potentially spinning the nucleus or altering its rotation unpredictably. And if the nucleus is a contact binary, two lobes loosely bound by gravity, tidal forces and thermal stress could separate them entirely. In this scenario, the Sun becomes a cosmic gatekeeper, testing the resilience of every object that passes through the inner solar system. Interstellar comets, formed in distant environments with potentially unique structural properties, might be especially fragile, or, conversely, unusually robust. The true answer will reveal itself only when the comet emerges from behind the Sun. A historical comparison is instructive. Comet Shoemaker-Levy 9 was torn apart by Jupiter's tidal forces during a close approach in 1992, fragmenting into more than 20 pieces that later collided with the planet in a spectacular display. Jupiter's gravity pulled the comet apart because the gradient across its diameter exceeded the comet's self-gravity. The Sun's tidal forces at the distance of 3I Atlas were much weaker, but a nucleus already stressed by heat or prior fragmentation might still fail where a stronger, intact comet would survive. The question now hangs over astronomers like a shadow. Has the Sun revealed a hidden vulnerability of interstellar visitors? The answer will depend entirely on what is observed when 3I Atlas reappears. If it emerges intact following its hyperbolic path with normal outgassing and dust production, the solar wind event becomes a historical footnote, dramatic but ultimately inconsequential. If it has broken apart or vanished entirely, the discovery could challenge our assumptions about the structural integrity of interstellar objects, their formation, and their resilience to solar forces. Astronomers mark their calendars, consult ephemerides, and prepare observation plans for the precise moment when 3I Atlas should once again become visible, ready to witness the outcome of this cosmic test. The timeline for 3I Atlas's reappearance depends on several factors. Its exact trajectory is uncertain due to non-gravitational forces, while its brightness could have shifted dramatically, and observing geometry determines how far from the Sun the comet must travel before telescopes can detect it against the glare of the sky. Current projections indicate the comet should emerge from solar conjunction in late October or early November 2025, reaching sufficient solar elongation, the angular separation from the Sun as seen from Earth, to become observable with specialized instruments. Initial recovery efforts will likely rely on space-based observatories capable of blocking the Sun's overwhelming light more effectively than ground-based telescopes. The Solar and Heliospheric Observatory, SOHO, uses coronagraphs to create artificial eclipses, allowing scientists to study regions near the Sun where comets often hide. Meanwhile, the Solar Terrestrial Relations Observatory, known as STEREO, operates 2 spacecraft in solar orbit, providing alternative viewing angles that might catch the comet earlier than Earth-based instruments. Humanity's Parker Solar Probe, currently the closest artificial object to the Sun, periodically travels within Mercury's orbit, encountering extreme solar wind conditions and temperatures. If its path coincided with 3I Atlas's position during conjunction, its instruments could have captured data in conditions impossible for Earth-based telescopes. Yet Parker's mission focuses on the solar corona and solar wind, not comets, and unless the comet crossed its narrow field of view at precisely the right moment, no data would be collected. Mission scientists have reported no fortuitous encounters, suggesting either the geometry was unfavorable or the comet remained too faint against the Sun's brilliance. What will the first recovery images reveal? In the best-case scenario, 3I Atlas emerges as expected, perhaps slightly fainter from dust loss, yet otherwise intact, with a visible coma and tail signaling active sublimation from the nucleus. Spectroscopic analysis would confirm familiar molecular signatures: water vapor, cyanogen, carbon monoxide, the chemical fingerprints that define cometary composition. Observations of tail length and structure would offer insights into gas production rates and solar wind conditions following conjunction. Astronomers would compare pre- and post-conjunction brightness to determine whether the comet lost significant mass during its closest solar approach. The worst-case scenario is more sobering. The comet may fail to appear at all, leaving an empty patch of sky where it should be. This would suggest total disintegration, the nucleus fragmented into pieces too small to detect individually, or vaporized entirely, leaving only a diffuse cloud of gas invisible against the solar background. While disappointing, such losses are not unprecedented. Numerous comets have vanished after close solar passes, providing critical data for understanding fragmentation physics. Between these extremes lies a spectrum of possibilities. The comet might return as multiple fragments, a string of condensations along its orbit indicating a nucleus that split but partially survived. Fragment streams are difficult to observe, as each piece is fainter than the original nucleus, yet they offer valuable insight into nuclear structure and breakup mechanics. Analysts would measure separation distances and velocities to reconstruct the timing and nature of the fragmentation. Another scenario is dormancy. The comet could have exhausted near-surface volatiles during its perihelion pass, leaving a darkened crust that prevents sublimation until solar heating cracks it, or erosion exposes fresh ice. Dormant comets resemble asteroids, showing no coma or tail, just a bare sunlit rock. If 3I Atlas goes dormant, we would lose the ability to study its gas composition, but we would gain insight into surface processes and the formation of insulating mantles. Yet the most intriguing possibility is unexpected brightening. Comets sometimes fragment in ways that expose fresh, volatile, rich material to sunlight, triggering sudden increases in gas production and overall brightness. A splitting nucleus can create new active areas, expanding the total sublimating surface. If 3I Atlas fragments and brightens simultaneously, the comet that re-emerges could be even more spectacular than the one that disappeared. Though spectacular, the fragments would likely fade quickly as their ice reserves are depleted. Spectral diagnostics will be critical. Pre-conjunction observations revealed typical signatures of water and perhaps carbon monoxide, but a complete spectral inventory was never obtained. Post-conjunction spectroscopy may detect species previously unseen, either because the comet wasn't producing them in measurable amounts, or because earlier observations didn't cover the right wavelengths. Emission lines of oxygen indicate water sublimation. Cyanogen, CN, traces carbon-nitrogen chemistry. Lines of sodium and iron occasionally appear, signaling exposure of metallic-rich material from the nucleus interior. Amateur astronomers may play a vital role in recovery efforts. A global network of backyard telescopes provides near-continuous sky coverage that professional facilities, constrained by observing schedules, cannot match. If 3I Atlas brightens unexpectedly or fragments into widely separated pieces, dedicated amateurs might be the first to spot it. Crowdsourced astronomy has grown increasingly significant, with digital cameras and software enabling amateurs to produce observations rivaling professional quality data. A live cosmic mystery is unfolding in real time, and anyone with a telescope and clear skies can participate. The comet could reappear at any moment, assuming it survived, or days could pass, then weeks, with nothing visible until astronomers reluctantly conclude that 3I Atlas is gone, destroyed by the Sun after travelling across interstellar space to visit our solar system. The uncertainty is maddening and exhilarating in equal measure. No probe was sent to intercept the comet. We have no way to search actively beyond pointing telescopes at its predicted location and waiting. All we can do is observe, speculate, and prepare for whatever emerges from the solar glare. A deeper question haunts the astronomical community. If the nucleus is gone, do we still have 3I Atlas? Or is it now merely debris, a dispersed cloud of dust and gas that once formed an interstellar comet, but no longer exists as a distinct object? Philosophically, it echoes the ship of Theseus paradox. If every plank of a wooden ship is replaced over time, is it still the same ship? If a comet fragments into 1,000 pieces, each following nearly the same orbit and carrying material from the original nucleus, are they collectively still the comet, or has it ceased to exist? There is no formal definition, only convention and convenience, and opinions vary depending on perspective. Yet the question matters. 3I Atlas represents something rare and irreplaceable, a sample from another star system. Losing it would be more than the disappearance of an astronomical target. It would sever a connection to something vast and distant, a thread linking humanity to the wider galaxy that we never fully grasped. Humans are natural pattern seekers, wired to find meaning, to connect events even when no connection exists. The simultaneous occurrence of a major solar event, the disappearance of an interstellar comet, and multiple large earthquakes on Earth triggered every alarm in our collective unconscious, a primal warning that something extraordinary is unfolding. The mainstream scientific position on links between solar activity and earthquakes is unambiguous. Earthquakes are driven by plate tectonics, the slow, inexorable motion of lithospheric plates atop the convecting mantle, by strain energy accumulating in the crust until it exceeds the friction locking faults in place. Solar activity has no credible mechanism to trigger these releases. Magnetic fields do not influence rock. Solar wind particles cannot penetrate to Earth's surface. They are deflected by the magnetosphere and atmosphere. The thermal energy delivered by sunlight is negligible compared to Earth's internal heat. Comprehensive analyses of earthquake catalogues searching for correlations with solar cycles or individual solar events reveal nothing beyond what would occur by chance. Yet patterns continue to appear in datasets, tantalizing alignments that never reach statistical significance but never vanish entirely. Some researchers at the edges of mainstream respectability explore possible mechanisms. Could solar-induced ionospheric disturbances subtly alter electrical properties in fault zones? Could tiny changes in Earth's rotation or magnetic field orientation, driven by solar wind momentum transfer, modulate tectonic stress just enough to tip a fault on the brink? Might magneto-hydrodynamic coupling between the ionosphere and conductive layers in the crust transmit energy in ways we don't yet comprehend? These hypotheses face immense skepticism. Extraordinary claims demand extraordinary evidence, and the evidence remains circumstantial at best. But the human mind does not operate on statistical thresholds. It works on narrative, on the stories that weave disparate events into a coherent whole. When the sun lashes out, earthquakes strike, and a comet vanishes all within the same news cycle, the narrative writes itself, even when the physics does not support it. The interstellar nature of 3I Atlas adds another layer of intrigue. These objects arrive from beyond our solar system, formed in alien environments with compositions and isotopic ratios potentially unlike anything in our neighborhood. They are literally alien, in the most precise sense. Humanity has always projected hope, fear, and imagination onto the unknown. When Oumuamua accelerated in ways that defied immediate explanation, speculation erupted. Artificial origin, alien probes conducting reconnaissance, technologies beyond comprehension. The simplest explanation, natural outgassing, remained, but the idea of an alien artifact captured public fascination in ways that dry scientific papers on sublimating carbon monoxide never could. 3. I-Atlas disappearing during a solar storm invites similar conjecture. Did the comet carry something that made it a target? Are we witnessing a cosmic quarantine, a solar system defense destroying interstellar visitors before they penetrate the inner system? The scientific absurdity of these ideas does not reduce their psychological appeal. We want the universe to harbor mysteries beyond orbital mechanics and spectroscopy. We want hidden meanings in celestial alignments. We want comets to be more than icy remnants. We want them to be messengers, bearers of knowledge, life, or purpose. The panspermia hypothesis, the idea that life spreads across the cosmos aboard comets and asteroids, provides a scientific framework for some of our deepest yearnings. If comets delivered the organic precursors that sparked life on Earth during the heavy bombardment billions of years ago, then every comet becomes a potential seed carrier. Interstellar comets take on even greater significance, as they may carry chemistry forged around other stars far beyond our solar neighborhood. The destruction of 3I Atlas, if that is what occurred, would be the loss of a priceless biological sample, a cosmic library consumed before we could read its contents. More exotic possibilities circulate in fringe communities. Advocates of the electric universe see the sun's violent interaction with the comet as proof of overlooked plasma physics. They point to unusual brightness variations, extreme solar wind, and disconnection events in other comet tails as evidence that electricity, not just gravity and thermal processes, shapes comet behavior. The mathematics behind their models rarely withstand rigorous scrutiny. Predictions often fail. Observations sometimes contradict expectations. Yet the visual drama of electric phenomena, lightning, sparks, and auroral displays ensures these ideas persist, captivating imaginations beyond the scientific shortcomings. Conspiracies inevitably emerge. Did space agencies withhold data from Parker Solar Probe's close encounters with the Sun? Were images or spectra of 3I Atlas taken during conjunction kept secret? What could motivate such concealment? Perhaps the comet behaved in ways that defied explanation, challenged fundamental assumptions, or frightened those who understood the implications. Maybe it fragmented unnaturally, emitted mysterious signals, or shifted course in ways that suggested control. These scenarios are exceedingly improbable, nearly impossible. Yet in minds predisposed to distrust official narratives, the absence of evidence becomes evidence of conspiracy. The psychological role of conspiracy theories is well understood. They offer the illusion of control in a universe ruled by randomness and chaos. They replace meaningless coincidence with hidden order, sometimes malevolent, providing comfort against the stark truth. Earthquakes strike without reason, comets disintegrate unpredictably, and we are but fragile consciousnesses on a tiny planet hurtling through an indifferent cosmos. The narrative of secret knowledge and suppressed truths is often more emotionally satisfying than the slow, patient work of scientific investigation, gradually converging on provisional conclusions. And yet, the universe occasionally aligns in ways that defy expectation. Coincidences sometimes appear too perfect to ignore, even when causation remains unproven. The October 2025 conjunction of events, the solar storm, the comet's disappearance, and multiple large earthquakes might be precisely that. A coincidence so improbable it demands attention, even if ultimately meaningless. Or it may hint at subtle, undetected connections, weak couplings between geophysical systems and space weather, operating below our current measurement thresholds. Science advances by investigating anomalies, not dismissing them. Researchers exploring solar earthquake correlations pursue legitimate, if speculative, science. Their efforts may uncover nothing, but the search itself holds value. When 3I Atlas emerges from behind the Sun, if it emerges, the comet that returns may not resemble the one that vanished. And when astronomers publish their observations, explanations grounded in physics, chemistry, and orbital mechanics will follow. Some will accept these analyses and move on. Others will linger on the mysteries that remain.